Picture this: a single, unimaginable explosion of energy and light, ripping through the darkness of nothingness. This was the Big Bang, the moment our universe roared into existence. A cosmic detonation so powerful it set the stage for everything that followed. But what if I told you that this was just the first in a series of violent, world-shaping encounters? That the universe, as we know it, wasn't just born in chaos, it was refined by it, sculpted by collisions so massive they rewrote the rules of reality itself. From the very beginning, the cosmos has been a battlefield. Planets, stars, even entire galaxies have clashed in epic, slow-motion crashes, each one leaving behind scars and stories etched into the fabric of space. Think about that for a second. Every time you look up at the night sky, you're staring at the aftermath of ancient cosmic wars, events so colossal they defy human comprehension. Some of these collisions were creative, birthing new worlds. Others were destructive, tearing apart what had once been whole. But all of them were essential, shaping the universe into the strange, beautiful place we call home today. And that's exactly what we're about to explore: 25 of the most incredible, mind-bending cosmic collisions ever discovered. From the titanic smash that might have given us our moon, to the galactic mergers that will one day rewrite our night sky, these aren't just distant scientific curiosities. They're the hidden architects of reality, the reason you and I even exist. So buckle up, because we're about to dive into the heart of chaos, tracing the echoes of these universe-altering impacts and uncovering their awe-inspiring legacies. Trust me, by the end, you'll never look at the stars the same way again. Let's rewind time all the way back to the very beginning, before stars, before galaxies, before even the simplest atoms existed. The Big Bang wasn't just a collision, it was the collision, an eruption of energy so vast it birthed time and space in a single, incomprehensible instant. Picture an unfathomable surge of heat and light, hotter than the core of any star, denser than the heart of a black hole, expanding faster than the speed of thought. In less than a fraction of a second, the universe went from a searing pinpoint to a churning ocean of raw potential, teeming with the building blocks of reality. But here's where it gets even wilder. The Big Bang wasn't just an explosion in space. It was the creation of space itself, stretching and warping as it expanded, carrying matter and energy along like debris on a cosmic tide. Within those first moments, particles collided and fused in a frenzy, forming the first protons and neutrons. By the time the universe was just 3 minutes old, the first atomic nuclei had already taken shape, setting the stage for everything that would follow. And yet, the most astonishing evidence of this primordial cataclysm isn't hidden in some distant galaxy. It's all around us, lingering in the faint glow of the cosmic microwave background. This afterglow, discovered by accident in the 1960s, is like a snapshot of the infant universe frozen in time. Its tiny temperature fluctuations reveal the seeds of future galaxies, the faint echoes of density variations that would one day grow into the vast structures we see today. The Big Bang didn't just set things in motion, it baked the rules of physics into the fabric of existence. Without that initial, violent expansion, there would be no gravity to shape stars, no chemistry to build planets, no atoms to form life. It's the ultimate reminder that every atom in your body, every speck of dust in the cosmos, traces its lineage back to that single, universe-defining moment. And if that doesn't make you pause, consider this: we're still riding the shockwave of that explosion, hurtling through an expanding universe that began with the biggest bang of all. Now fast forward a few 100 million years, our young Earth is still a molten hellscape, battered by asteroids and simmering with volcanic fury. But the solar system was far from stable, and disaster was brewing. Enter Theia, a wandering protoplanet roughly the size of Mars, hurtling through space on a collision course with our world. This wasn't just a glancing blow, it was a head-on, planet-shattering impact. Theia struck Earth with such force that it didn't just crack the surface, it vaporized entire layers of both worlds, sending a colossal plume of molten rock and metal screaming into orbit. For hours, rivers of superheated debris circled the planet like a furious, glowing halo. And then gravity took over. Over decades, that scattered debris began clumping together, drawn into a swirling disk that eventually coalesced into a single, rocky sphere, our Moon. But this wasn't just any satellite. The Moon's birth had profound consequences for Earth. Its gravity stabilized our planet's wobbly rotation, preventing wild climate swings that could have made life impossible. The lunar tides may have even churned Earth's primordial oceans, stirring the chemical soup that eventually led to the first living organisms. Here's what's even wilder: we carry traces of Theia inside us. Scientists believe chunks of the doomed protoplanet sank into Earth's mantle, where they might still linger today. And when astronauts brought back moon rocks, they found something astonishing. Their composition matched Earth's mantle almost exactly, like cosmic fingerprints proving this violent shared history. So next time you gaze at the Moon, remember it's not just a silent companion in the night sky. It's the scar of an ancient catastrophe, a monument to the brutal forces that shaped our world. Without that apocalyptic collision, Earth might have been just another barren rock spinning alone in the dark. Instead, we got a partner in the cosmic dance, one that guided the evolution of life itself. Just when Earth thought it had survived its most violent cosmic encounter, the universe had other plans. Around 4 billion years ago, long after the Moon had formed, our planet found itself in the crosshairs of an even more relentless assault: the Late Heavy Bombardment. This wasn't just a few stray asteroids. Imagine a celestial hailstorm with thousands of giant space rocks screaming through the inner solar system, slamming into Earth and its neighbors with terrifying frequency. Craters the size of cities erupted across the surface, turning the young planet into a pockmarked battleground. But here's the twist: this cosmic punishment may have been a blessing in disguise. Those collisions didn't just bring destruction, they delivered the ingredients for life itself. Locked within the icy cores of comets and water-rich asteroids were molecules we now recognize as essential: water, carbon, even amino acids. Every time one of these objects smashed into Earth, it wasn't just leaving a scar, it was depositing the raw materials for oceans, atmospheres, and eventually the first stirrings of biology. Scientists call this the panspermia hypothesis, the idea that life's building blocks hitchhiked across the cosmos on these ancient impactors, and the evidence is striking. Meteorites recovered today still contain traces of organic compounds, some as complex as nucleobases, the very letters in DNA's genetic alphabet. It's as if the universe was trying to write the recipe for life in the rubble of its own violence. The Late Heavy Bombardment didn't just reshape Earth's surface, it rewrote its destiny. Without those impacts, our planet might have remained a dry, barren rock. Instead, the collisions filled vast basins with water, creating the first primordial seas where chemistry could experiment with life. Even more astonishing, the same bombardment likely struck Mars and Venus, meaning the seeds of life may have been sown across multiple worlds. Only on Earth, thanks to a delicate balance of factors, did those seeds take root. So when you take a sip of water or feel the rain on your skin, remember, you're touching relics of an ancient cosmic storm. The same cataclysm that once turned the solar system into a shooting gallery also handed us the keys to existence. It's a humbling thought. The very things that could have erased us may have been the ones that made us possible. Mercury has always been the solar system's oddball: small, scorched, and strangely dense, with a metallic core that makes up nearly 85% of its volume. For decades, scientists scratched their heads over how a planet this close to the Sun could have such a massive metal heart while being wrapped in such a thin, rocky shell. The answer: a cataclysmic hit-and-run collision, so violent it ripped Mercury's outer layers clean off and left behind a planetary core masquerading as a world. This is the giant impact hypothesis, a brutal origin story that begins with a young Mercury, not much different from Earth or Venus in its early days. Picture a protoplanet covered in molten rock and metal, its surface still cooling from the chaos of the solar system's formation. Then, disaster strikes. A rogue body, possibly as large as Mercury itself, comes screaming in at thousands of miles per hour. The impact wasn't a direct hit. It was more like a cosmic sideswipe, a glancing blow that nonetheless unleashed enough energy to vaporize rock and send debris flying into space. Here's where things get fascinating. Unlike Earth's collision with Theia, which left behind enough debris to form the Moon, Mercury's smash-up was more like a robbery. The force of the impact didn't just eject material, it launched it at escape velocity, hurling it beyond Mercury's gravitational grasp forever. What remained was a stripped-down, metal-rich husk, its outer layers lost to the void. This theory explains so much: Mercury's abnormally high density, its lack of a substantial mantle, even its bizarre magnetic field. All of them fit the profile of a planet that survived a cosmic scalping. And it's not alone. Similar collisions might explain other oddities in our solar system, like Mars' lopsided northern lowlands or the way Uranus spins on its side. But Mercury's case is special because it challenges our assumptions about planetary formation. Think about it. We often imagine planets growing steadily, accumulating layers like an onion. But Mercury's story flips that idea on its head. Sometimes planets evolve by losing, not gaining. They're sculpted by violence, reshaped by accidents that leave them forever changed. And if a single impact could turn a would-be Earth into a metal-clad oddity, what does that say about the untold stories of exoplanets out there, worlds we've yet to discover? The scars of Mercury's collision aren't just relics of the past. They're clues written in gravity and geology, waiting to teach us how chaos and chance built the solar system we call home. Venus stands as a warning, a world that might have once been Earth's twin, now a blistering wasteland shrouded in toxic clouds. But how did our sister planet become such a nightmare? The answer could lie in a collision so violent it didn't just scar Venus, it flipped the planet upside down. Most planets spin counterclockwise, a relic of the swirling disk that birthed them. Venus defies this rule, rotating backward in what astronomers call a retrograde spin. And it's not just slow, it's agonizingly sluggish, with a day longer than its year. For decades, this bizarre behavior puzzled scientists. Then came the radical theory: a protoplanet, perhaps as large as Earth, smashed into Venus with enough force to stop its original rotation dead in its tracks, then send it spinning the wrong way. The math is chilling. Models show an impactor striking Venus at a precise angle could have imparted enough torque to reverse its spin. The collision wouldn't just alter its rotation, it would liquefy the crust, vaporize oceans if they existed, and churn the atmosphere into a superheated maelstrom. Debris from the crash might have even coalesced into a short-lived moon, later torn apart by tidal forces. But the real horror came afterward. Without a stabilizing magnetic field, possibly destroyed in the impact, Venus's oceans evaporated under relentless solar radiation. Water vapor, a potent greenhouse gas, flooded the skies, trapping heat in a runaway cycle. Carbon dioxide built up as volcanic eruptions pumped more into the atmosphere, unchecked by oceans or life to absorb it. Over millennia, temperatures soared to 900 degrees Fahrenheit, hot enough to melt lead. Here's the eerie part: Venus might not have always been a hellscape. Recent climate models suggest early Venus could have had shallow oceans and temperate conditions until a collision reset its destiny. The same impacts that delivered water to Earth may have boiled it away on Venus, all because of one disastrous cosmic strike. What makes this theory so compelling isn't just the mechanics, it's the implications. Venus shows us how fragile planetary balance can be. A single violent event didn't just change its rotation, it triggered a cascade of disasters, turning a potential paradise into a cautionary tale. And if it happened there, could it happen elsewhere? As we discover exoplanets with retrograde spins, Venus stands as a reminder. In the cosmos, sometimes fate hinges on one catastrophic moment. Mars wears its trauma like a badge. Half of its surface lies smooth and low, while the other half rises in rugged, cratered highlands. This stark split, known as the Martian dichotomy, isn't just a quirk of geography. It's the signature of a cataclysm so violent it may have reshaped the entire planet. Imagine an object the size of Earth's moon, slamming into Mars' northern hemisphere with the force of 1,000,000 nuclear bombs. The impact wouldn't just leave a dent, it would fracture the crust, melt vast regions, and send shockwaves rippling through the planet's core. The evidence is written in the land itself. The northern lowlands are younger, with fewer craters, suggesting a resurfacing event erased ancient scars. Meanwhile, the southern highlands are pockmarked and ancient, preserving billions of years of cosmic battering. But here's the twist: gravity maps reveal something startling. The crust beneath the northern plains is thinner, as if something had scraped it away. Combine that with seismic data from landers and the picture becomes clear. Mars didn't evolve this way. It was remade. This collision didn't just alter Mars' face, it may have stolen its future. The impact could have disrupted the planet's magnetic field, shutting down the dynamo in its core. Without that protective shield, solar radiation stripped away the atmosphere over eons, turning rivers to dust and oceans to vapor. Some scientists even argue the collision triggered massive volcanic eruptions, like those that built Olympus Mons, by weakening the crust and releasing pent-up magma. Yet there's another possibility. What if the northern basin wasn't carved by a single strike, but by a series of smaller impacts? Some models suggest a swarm of asteroids could have pummeled the region, collectively sculpting the lowlands. It's a debate that splits planetary scientists, but either scenario leads to the same haunting conclusion. Mars' fate was sealed by violence, and that raises a chilling question. If impacts can transform a world so completely, how many other planets out there bear similar invisible scars? Mars stands as a silent testament, a world where one catastrophic moment turned potential into ruin, leaving behind a landscape forever divided between what was and what might have been. Between Mars and Jupiter, where a planet could have been, lies a cosmic graveyard, the asteroid belt. This sprawling field of rubble isn't just random debris. It's the wreckage of a future that never was, a world that never formed thanks to Jupiter's gravitational bullying and a series of violent, fragmenting collisions. Picture the early solar system, a chaotic construction zone where dozens of protoplanets jostled for space. In the belt's region, multiple rocky bodies were growing, on their way to merging into a proper planet. But Jupiter, the solar system's heavyweight champion, had other plans. Its immense gravity stirred the region like a spoon in a boiling pot, yanking protoplanets into unstable orbits. Instead of gently merging, these bodies found themselves on collision courses, smashing together at speeds too fast to stick, shattering rather than growing. The scars of this demolition derby are still visible today. Take Vesta, one of the largest asteroids, a 500-kilometer-wide remnant with a colossal crater gouging its southern pole. That impact was so powerful it nearly split Vesta apart, sending shockwaves through its structure and spraying fragments across the solar system, some of which eventually landed on Earth as meteorites. Then there's Ceres, the belt's lone dwarf planet, a survivor that may have been on its way to becoming a proper planet before Jupiter's interference stunted its growth. But here's the twist: the asteroid belt isn't packed shoulder to shoulder like sci-fi movies suggest. The average distance between objects is vast, millions of kilometers. That emptiness is another clue to its violent past. Most of the original material was either ejected by Jupiter, swallowed by the Sun, or pounded into dust. What's left are the stragglers, the few durable remnants that avoided annihilation. This story isn't just about destruction, though. The belt's chaos may have shaped life's chances on Earth. When Jupiter destabilized the region, it sent a flood of water-rich asteroids careening inward, possibly delivering the oceans to our planet. So while Jupiter robbed the solar system of one world, it might have given us the ingredients for ours. The asteroid belt isn't a failed planet. It's a monument to how violence and gravity wrote the rules of our cosmic neighborhood. For centuries, Jupiter has played the role of Earth's cosmic shield, its immense gravity deflecting or swallowing dangerous debris before it can reach the inner solar system. But in 1994, humanity got front-row seats to this protective dance in action when comet Shoemaker-Levy 9, torn into fragments by Jupiter's tidal forces, plunged into the gas giant's atmosphere in a fiery spectacle visible from Earth. This wasn't just a single impact. Over 6 days, 21 comet fragments, some over 2 kilometers wide, slammed into Jupiter's southern hemisphere at speeds exceeding 200,000 kilometers per hour. Each strike unleashed an explosion equivalent to millions of megatons of TNT, gouging temporary scars in Jupiter's clouds larger than Earth itself. The largest fragment, Fragment G, created a fireball so intense it briefly outshone the planet's moon Io, rising 3,000 kilometers above the cloud tops. But what made Shoemaker-Levy 9 revolutionary wasn't just the light show, it was the science. For the first time, astronomers witnessed a planetary collision in real time, tracking the aftermath with telescopes like Hubble. The impacts churned up material from deep within Jupiter's atmosphere, revealing molecules like sulfur and ammonia normally hidden beneath the upper clouds. They also left behind dark, sooty smudges, carbon compounds forged in the extreme heat of the explosions which lingered for months, drifting in Jupiter's violent winds. Perhaps most crucially, this event became a wake-up call for planetary defense. If fragments of a single comet could unleash that much energy on Jupiter, what would a similar impact do to Earth? Suddenly, the threat of near-Earth objects wasn't theoretical, it was tangible. Governments ramped up efforts to catalog asteroids and comets, leading to programs like NAS, a Planetary Defense Coordination Office. Shoemaker-Levy 9 didn't just scar Jupiter, it reshaped how we view our own vulnerability in the cosmos. Yet the comet's legacy goes deeper. Those impacts proved gas giants aren't just static balls of gas. They're dynamic worlds where even cataclysmic collisions fade into the swirling atmosphere, absorbed without lasting scars. Jupiter endured this cosmic bombardment the way it's endured billions of years of chaos by being a gravitational titan, a cosmic vacuum cleaner for the solar system's debris. And as we watch similar impacts on exoplanets light years away, Shoemaker-Levy 9 remains a reminder. Sometimes witnessing destruction teaches us how to survive it. Saturn's rings gleam like a cosmic jeweled necklace, but their beauty hides a violent past. For centuries, astronomers assumed they were as ancient as the solar system itself, until closer inspection revealed a shocking truth. These iconic bands of ice and rock might be surprisingly young, possibly forming just 100 million years ago when dinosaurs still roamed Earth. The question is, what cataclysm could have created such a spectacular structure so recently? One leading theory points to a moon torn apart. Picture a medium-sized icy body, perhaps as large as Saturn's current moon Mimas, drifting too close to the gas giant. As tidal forces overwhelmed its gravity, the moon would have been stretched and shredded, its fragments scattering into orbit. Over time, collisions between those fragments would have ground them into smaller pieces, eventually sculpting the rings we see today. Supporting this idea are Cassini mission observations. The rings are remarkably pure ice, suggesting they haven't been contaminated by interstellar dust over billions of years. But there's another, even more dramatic possibility, a colossal collision between two icy protoplanets. Imagine two worlds, each several times the mass of Pluto, smashing together near Saturn. The impact wouldn't just shatter them, it would vaporize vast amounts of ice, creating a temporary disk of molten debris. As this material cooled, it could have condensed into countless icy particles, their orbits gradually flattening into the razor-thin rings we observe. Computer simulations show this scenario perfectly explains the rings' composition and their abnormally high cleanliness. Here's where it gets stranger. Some researchers argue both theories might be true just at different times. Saturn could have had multiple ring systems throughout its history, each born from a separate disaster and later erased. The current rings might simply be the latest in a series of temporary cosmic artworks, destined to fade as debris spirals into the planet or escapes into space. What makes this mystery so captivating isn't just the science, it's the implications. If rings can form and vanish over cosmic timescales, we might be witnessing Saturn's jewelry during a rare, fleeting moment. Elsewhere in the universe, gas giants could be cycling through ringed and ringless phases like celestial fashion trends. And if collisions built these structures, then every glittering ring in the night sky isn't just decoration, it's a monument to some forgotten cataclysm, a frozen echo of violence turned into beauty. Uranus doesn't play by the rules, it rolls. While every other planet in the solar system spins like a top, Uranus lies nearly sideways, its axis tilted a staggering 98 degrees. Picture a world where the sun doesn't rise and set but circles the sky like a Ferris wheel, where each pole gets 42 years of continuous daylight followed by 42 years of darkness. This isn't just a quirky accident, it's the cosmic equivalent of a knockout punch, a planetary haymaker so brutal it sent Uranus reeling, the leading theory. A cataclysmic collision with an Earth-sized protoplanet in the early solar system. Imagine a young Uranus spinning normally when a rogue world comes streaking in at an angle. The impact wouldn't just nudge the planet, it would deliver a glancing blow powerful enough to tip it onto its side, like a billiard ball struck off-center. Computer simulations show the math adds up. A strike from an object 2 to 3 times Earth's mass, hitting at around 20,000 miles per hour, could produce Uranus' extreme tilt. The collision might have even vaporized part of the planet's icy mantle, scattering debris that later coalesced into its unusual moons, and those moons hold critical clues. Unlike other gas giants with orderly, equatorial satellite systems, Uranus' moons orbit in the same tilted plane as its rotation, as if frozen in the moment of impact. Their compositions suggest they formed from the wreckage of the collision, a family of orphans born from chaos. Even Uranus' magnetic field is off-kilter, wobbling asymmetrically and offset from the planet's center, possibly a scar from the impact disrupting its internal dynamo. But the real shocker is the aftermath. Uranus' tilt created the most extreme seasons in the solar system. During solstice, one pole bakes under constant sunlight while the other plunges into a frigid decades-long night. This wild temperature swing might explain why Uranus' atmosphere is oddly calm compared to other gas giants. Its energy gets redistributed in ways we're still struggling to model. Here's what makes this mystery so tantalizing. If a single collision could redefine an entire planet's destiny, how many other worlds out there bear similar hidden scars? Uranus forces us to rethink planetary evolution not as a gentle process, but as a series of violent accidents that leave worlds forever changed. So the next time you see Uranus labeled as the boring ice giant, remember, its tilt is anything but dull. It's a fossilized record of one of the solar system's most brutal showdowns. Neptune's largest moon, Triton, is a cosmic imposter, a celestial refugee that doesn't belong. Unlike every other major moon in the solar system, Triton orbits backward, moving in the opposite direction of Neptune's rotation. This rebellious path is the smoking gun of a violent past, evidence that Triton didn't form alongside the ice giant but was kidnapped from the depths of space. Picture the early solar system teeming with icy bodies beyond Neptune's orbit. Triton, originally a free-flying dwarf planet in the Kuiper belt, was minding its own business until a fateful encounter altered its trajectory. One prevailing theory suggests Triton strayed too close to Neptune as part of a binary pair, two objects gravitationally bound together. When Neptune's gravity ripped them apart, one was flung into the void while Triton, robbed of its momentum, spiraled into a tight, backward orbit. But there's a darker possibility, a direct collision. Triton might have once had a twin, a companion body that smashed into Neptune or another moon, bleeding off enough energy for the ice giant to seize Triton permanently. Either way, the capture would have been catastrophic. The gravitational forces involved would have stretched and heated Triton's interior, melting its icy shell and triggering volcanic activity that persists to this day. And that's where things get even more fascinating. Despite its frozen surface, Triton is far from dead. NASA Voyager 2 spotted geysers erupting nitrogen gas and dark dust plumes up to 8 kilometers high, a sign of subterranean heat defying the moon's frigid -235 degrees Celsius exterior. These cryovolcanoes hint at a subsurface ocean, kept liquid by tidal forces as Triton's stretched orbit flexes its core like putty. Yet Triton's defiance comes at a cost. Its retrograde orbit is a death sentence. Neptune's gravity drags the moon closer by about 3.5 centimeters each year. In a billion years, Triton will either plunge into the planet's atmosphere or be torn apart, forming a dazzling ring system. For now, it remains a captured anomaly, a frozen rebel with a violent history and an inevitable demise. What makes Triton's story so compelling isn't just its past, it's what it reveals about the chaos of planetary migration. If a world as massive as Triton could be hijacked, how many other moons across the galaxy are stolen survivors? Every time we study its geysers or map its cantaloupe-like terrain, we're glimpsing the untold saga of cosmic piracy, where gravity rewrites destinies and nothing stays where it began. Pluto may be small, but its history packs a cosmic punch. Out in the frozen reaches of the Kuiper Belt, far from the sun's warmth, this dwarf planet and its entourage of moons tell a story written in collisions, one so dramatic it reshaped an entire miniature solar system. At the heart of Pluto's chaotic past is Charon, its largest moon. Charon isn't just a companion, it's a piece of Pluto itself, torn free in a cataclysmic impact billions of years ago. Picture this, a proto-Pluto still forming when a Kuiper Belt object roughly the size of Pluto's current mass comes barreling in. The collision wouldn't have been a direct hit, but a glancing blow powerful enough to splinter Pluto's outer layers, sending debris spiraling into orbit. Over time, gravity gathered that debris into Charon, a moon so massive it doesn't even orbit Pluto instead. Both worlds dance around a shared center of gravity in empty space, locked in a gravitational tug of war. But Charon isn't the only clue to this violent origin. Pluto's smaller moons, Styx, Nix, Kerberos, and Hydra, are like celestial confetti, their irregular shapes and chaotic orbits hinting at a system sculpted by impact. New Horizons' 2015 flyby revealed their surfaces are startlingly bright, suggesting they're coated in pristine water ice flung outward during the collision. Even Pluto's heart-shaped glacier, Tombaugh Regio, might be a relic of that ancient trauma, a vast basin where the impactor struck, later filled with sluggish nitrogen ice. What's truly astonishing is how much this tiny system mirrors the early solar system's chaos. The Kuiper Belt isn't just a quiet freezer at the edge of the sun's domain. It's an unfinished construction zone where dwarf planets like Pluto and Haumea bear the scars of forgotten cosmic brawls. Haumea, for instance, spins so fast it's stretched into an ellipsoid, likely after a massive collision birthed its own moons. These impacts didn't just shape worlds, they created entire families, proving that even in the solar system's farthest reaches, violence writes the rules. New Horizons didn't just give us snapshots of Pluto, it handed us a forensic toolkit. By analyzing the composition of Pluto's surface ices and Charon's water-rich crust, scientists pieced together a timeline of that fateful collision. The shock of the impact could have briefly melted Pluto's interior, creating an underground ocean that might still linger today, locked beneath layers of insulating ice. And if that's true, it raises a tantalizing possibility. Even in the wreckage of cosmic violence, the ingredients for life might find a way. So when you look at Pluto's fuzzy image through a telescope, remember, you're not just seeing a lonely ice ball. You're witnessing a survivor, a world remade by catastrophe, surrounded by the shattered pieces of its own past. And out in the Kuiper Belt's darkness, countless other Pluto-like worlds likely share similar origin stories, silent witnesses to the collisions that built the solar system's final frontier. Far beyond the orbits of Neptune and Pluto, in the deepest, darkest reaches of our solar system, lies a frozen reservoir of ancient ice and rock, the Oort cloud. This vast spherical shell, stretching nearly a light-year from the Sun, is home to trillions of icy remnants left over from the solar system's birth. Most will never leave their distant orbits, but every so often, gravitational whispers from passing stars or the gentle nudge of a galactic tide sends one of these frozen wanderers spiraling inward, transforming it into a dazzling and sometimes destructive long-period comet. These comets aren't like the short-period ones that swing by every few decades. Long-period comets arrive from the Oort cloud like messengers from the void, tracing wild, elongated orbits that can take millions of years to complete. And when they finally streak through the inner solar system, they bring with them pristine material unchanged since the Sun first flickered to life. So what flings these icy nomads our way? The answer lies in the delicate gravitational ballet of the galaxy. A star passing even a light year away can tug just hard enough to dislodge an Oort cloud object from its frozen slumber. Collisions between these distant bodies, though rare, can also send shards careening sunward. Even the Milky Way's own gravity plays a role. As the solar system bobs up and down through the galactic plane, tidal forces stir the Oort cloud like a spoon in coffee, occasionally loosening comets from their orbits. The most famous of these visitors, Comet Hale-Bopp, arrived in 1997 with a brilliance visible to the naked eye for over 18 months. Its hyperbolic orbit suggests it might never return, a one-time spectacle born from a chance gravitational nudge tens of thousands of years ago. Others, like the Great Comet of 1843, left behind ion tails so long they stretched across half the sky before vanishing forever into interstellar space. But these icy wanderers aren't just celestial fireworks. They're time capsules carrying clues about how planets formed and how water reached Earth. Some scientists believe long-period comets could have seeded our world with organic molecules, even as others delivered cataclysmic impacts. Every time one appears, it's a fleeting glimpse into the solar system's frozen attic, and a reminder that even in the deepest dark, gravity's invisible hand is always shuffling the cosmic deck. Right now, the Andromeda galaxy is rushing toward us at nearly 400,000 kilometers per hour, a cosmic inevitability set in motion by the unrelenting pull of gravity. But don't panic just yet. This isn't some apocalyptic head-on crash. It's more like a slow-motion ballet, a gravitational dance that will unfold over billions of years. When the Milky Way and Andromeda finally meet, their collision won't be a fiery explosion of stars. It'll be a ghostly pas de deux, two vast spirals merging into something entirely new. Here's the astonishing part. Space is so empty that even when galaxies collide, their stars rarely smash into each other. The average distance between stars in Andromeda is about 4.5 light years, meaning most will glide past one another like ships in the cosmic dark. Instead of violent impacts, the real drama will unfold in the gravitational tides. As the galaxies first brush past each other, their spiral arms will stretch and warp, flinging stars into long, shimmering streams across the sky. Some will be ripped from their orbits entirely, cast adrift into intergalactic space. Others will be slingshotted toward the galactic cores, feeding supermassive black holes that will flare to life as they devour this sudden feast. From Earth's perspective, assuming humanity is still around, the night sky will transform into something unrecognizable. Andromeda, currently a faint smudge in the constellation of the same name, will grow larger and brighter as it approaches. By the time the galaxies begin their first close pass, it could span half the sky, its dust lanes and star clusters visible even in twilight. As the merger progresses, new patterns of stars will emerge, a celestial kaleidoscope rearranged by gravity's invisible hand. Yet amid this chaos, life could persist. Computer simulations suggest our solar system might be flung farther from the galactic core, a mixed blessing. While we'd lose the dense star fields of the inner Milky Way, we'd also be safer from the radiation bursts of colliding gas clouds and black hole eruptions. The real threat won't be the merger itself, but the aftermath, a revitalized era of star formation as colliding gas clouds ignite new stellar nurseries. Supernova could become frequent, bathing nearby systems in lethal radiation. The end result, a brand new galaxy dubbed Milky Way-Andromeda by astronomers, a massive elliptical blob of stars devoid of spirals but glowing with the combined light of two ancient rivals. And somewhere in its outskirts, our sun, now a faint white dwarf, might still linger, a silent witness to the greatest cosmic merger in our corner of the universe. Our Milky Way didn't start as the grand spiral we know today. It built itself through a series of cosmic heists, swallowing smaller galaxies whole and absorbing their stars into its ever-growing body. One of its most dramatic meals happened nearly 10 billion years ago when a dwarf galaxy called Gaia Enceladus, or the Gaia Sausage, as astronomers whimsically nicknamed it, slammed into the infant Milky Way. The collision wasn't just a merger, it was a galactic overhaul, reshaping our galaxy's destiny in ways we're only beginning to unravel. The evidence for this ancient smash-up is written in the stars themselves. Using data from the Gaia Space Telescope, scientists noticed something peculiar, a population of stars moving backward against the Milky Way's rotation. These stellar rebels weren't just oddballs, they were invaders, remnants of Gaia Enceladus' core, scattered like cosmic confetti during the collision. Their chemistry told the same story. Unlike the Milky Way's native stars, rich in heavier elements, these interlopers were metal-poor, a signature of the smaller, slower-evolving galaxy they once called home. But the real shock was how much this merger reshaped the Milky Way's structure. Before the collision, our galaxy was likely a flat, orderly disk. The impact sent shockwaves through its gas and stars, puffing up the disk into the thick, star-studded bulge we see at the galaxy's heart today. Some simulations suggest the violence even triggered a frenzy of star formation, flooding the Milky Way with new stellar nurseries. And the chaos didn't stop there. The collision's gravitational aftershocks might have flung stars into the galaxy's outer halo, where they still orbit today as silent witnesses to the carnage. Yet Gaia Enceladus wasn't the Milky Way's only victim. The nearby Sagittarius dwarf spheroidal galaxy has been orbiting our galaxy for billions of years, slowly being torn apart by tidal forces. Each time it swings close, it leaves behind streams of stars, looping around the Milky Way like celestial spaghetti. These mergers aren't just historical footnotes, they're ongoing processes, still shaping the galaxy's evolution. Here's the wildest part, we're made of this chaos. Many of the Milky Way stars, and possibly even our sun, owe their existence to those ancient collisions. The gas and dust stirred up by mergers provided the raw material for new generations of stars, planets, and eventually us. So when you gaze up at the night sky, you're not just looking at a static tapestry of light. You're seeing a living, evolving mosaic, a galaxy built one violent merger at a time. Gliding through space in Andromeda's shadow is a cosmic oddball, the small, dense galaxy known as M32. At first glance, it seems unremarkable, a compact smudge of light easily overshadowed by its colossal neighbor. But peel back the layers, and M32 reveals itself as something far more dramatic, a galactic survivor, the stripped-down core of what was once a much larger galaxy torn apart by Andromeda's gravitational wrath. The clues are etched into M32's very structure. Unlike typical dwarf galaxies which sprawl loosely, M32 is unnaturally dense, packing billions of stars into a region just 1/10 the size of the Milky Way's core. It also lacks the usual halo of dark matter and ancient stars that should surround such a massive object. This suggests a violent past, one where Andromeda's tides ripped away its outer layers, leaving behind only the most tightly bound stars, like a fruit peeled down to its pit. Even more telling is the debris field. Surrounding Andromeda, astronomers have spotted vast streams of stars' ghostly tendrils arcing through space like cosmic breadcrumbs. These stellar rivers, rich in metal-poor stars, align perfectly with simulations of a galaxy being shredded over billions of years. The sheer scale of this wreckage implies the original galaxy was at least 20 times more massive than M32 is today, possibly as large as the Milky Way when it first ventured too close to Andromeda. But here's what makes this discovery so chilling. M32 isn't just a relic, it's a preview. In 4 to 5 billion years, the Milky Way will face a similar fate when it collides with Andromeda. While our galaxy's spiral arms will stretch and snap, its core, like M32, might endure, compressed and reshaped by the encounter. Stars ripped from the Milky Way could form new streams, mirroring those we see around Andromeda today. And just as M32 now orbits its captor, the remnants of our galactic center might one day circle the merged heart of Milkomda. Yet M32's story isn't just about destruction. Its survival hints at a universal truth. In the cosmos, even the most violent encounters can leave behind something enduring. Stripped of its past, M32 has become a laboratory for studying supermassive black holes, hosting one of the closest known examples to Earth. Its stars, though crowded, are a time capsule of the original galaxy's chemistry, offering clues to how such systems form and evolve under extreme conditions. So while M32 may be a ghost of its former self, it's far from a silent one. Every observation peels back another layer of its dramatic history, and in doing so, gives us a glimpse of the Milky Way's own inevitable metamorphosis. The universe doesn't just build galaxies, it remakes them over and over in collisions that reshape destiny itself. Somewhere in the constellation Corvus, 60 million light-years from Earth, two galaxies are locked in a slow-motion wreck, the Antennae galaxies. Named for the long, streaming tails of stars flung outward by their gravitational dance, this pair represents one of the most spectacular collisions ever captured by the Hubble Space Telescope. What makes this cosmic crash so remarkable isn't just its visual drama. It's a living laboratory showcasing how galaxies evolve, merge, and ignite bursts of new stars in the process. Before their collision, these were likely two unremarkable spiral galaxies minding their own business. But gravity had other plans. As they first grazed each other hundreds of millions of years ago, their mutual pull stretched and distorted their shapes, warping spiral arms into long, glowing ribbons. Now, in Hubble's iconic images, we see them at their most chaotic, their cores circling ever closer while colossal clouds of gas slam together, triggering fireworks of star formation. Regions that appear blue in the images are nurseries where thousands of young, searing hot stars have lit up, their intense radiation ionizing surrounding hydrogen gas into vibrant pink hues. Yet the real spectacle lies in what's invisible to the naked eye. Hidden within those glowing gas clouds are superstar clusters, dense groupings of newborn stars so packed together that some may one day rival the size and brilliance of globular clusters. These clusters are the universe's way of turning chaos into creation, compressing scattered gas into stellar factories under the extreme pressures of collision. And it's not just stars being born. The turbulent environment has likely birthed countless planets, though any life there would face a hostile world bathed in intense radiation from nearby supernova. The antennae galaxies also offer a glimpse into our own future. In a few billion years, when the Milky Way and Andromeda collide, a similar frenzy of star formation will erupt, though likely on an even grander scale. But here's the twist. The antennae's fate is already sealed. Eventually, their cores will merge into a single, massive elliptical galaxy, their once distinct structures erased by gravity's relentless pull. The dazzling star-forming regions will fade as gas is exhausted or blown away, leaving behind a quieter, older galaxy, a celestial phoenix risen from the ashes of its former self. What makes Hubble's observations so invaluable isn't just the beauty they capture, but the data they provide. By studying the antennae, astronomers have refined models of how gas behaves during mergers, how star clusters form under extreme conditions, and even how supermassive black holes at galactic centers interact before coalescing. Every wavelength of light, from X-rays tracing superheated gas around black holes to infrared revealing dust-shrouded star birth, adds another piece to the puzzle. So while the antennae galaxies may seem like a distant spectacle, they're far more than that. They're a time-lapse preview of the universe's relentless creativity, where destruction and birth are two sides of the same cosmic coin. And as we watch their slow-motion merger unfold, we're reminded the universe doesn't just build galaxies. It remakes them again and again, in collisions that blaze with both violence and beauty. The Mice galaxies, officially known as NGC 4676, paint a mesmerizing portrait of cosmic drama frozen in time. Located 300 million light-years away in the constellation Coma Berenices, these two spiral galaxies are locked in an intricate gravitational waltz, their long, sweeping tails of stars and gas stretching across the void like the slender tails of celestial rodents. What makes this collision so fascinating isn't just its striking appearance, it's a snapshot of a pivotal moment in galactic evolution, a before and after image of how mergers reshape the universe. As the galaxies spiral closer, their mutual gravity tugs fiercely at their structures, peeling away streams of stars and gas in opposite directions. These tidal tails, each spanning hundreds of thousands of light-years, are more than just debris. They're highways of redistributed matter, scattering stellar material far beyond the galaxy's original borders. Within these tails, pockets of dense gas collapse under their own gravity, igniting bursts of newborn stars that glow like diamonds strewn across the darkness. Yet the real spectacle is unfolding in the galaxy's cores, where swirling clouds of hydrogen gas collide, triggering superheated shockwaves that ignite even more intense star formation. The Mice also offer a rare glimpse into the asymmetry of galactic collisions. One galaxy appears relatively intact, its spiral arms only slightly distorted, while its partner is visibly mangled, its core stretched and warped by the encounter. This imbalance reveals how no two mergers are alike. The angle of impact, the size of the galaxies, and even their internal structures dictate how violently they reshape one another. Over the next few 100 million years, the Mice will continue their dance, their tails growing longer as their cores draw nearer, until they eventually merge into a single, unrecognizable elliptical galaxy. But here's what truly sets this collision apart. It's a living lesson in galactic recycling. The stars and gas torn loose by the merger won't vanish. They'll either drift into intergalactic space as lone wanderers or fall back into the newly formed galaxy, fueling future generations of stars. In a way, the Mice are a microcosm of the universe's endless cycle of destruction and rebirth, where even the most violent encounters sow the seeds of new beginnings. Through telescopes like Hubble, we're not just watching a distant spectacle, we're witnessing the fate of our own Milky Way, a preview of what awaits when our galaxy tangles with Andromeda. The Mice galaxies remind us that beauty in the cosmos often arises from chaos, and that even in the vast emptiness of space, no galaxy is ever truly alone. Stretching across 420 million light-years in the constellation Draco, the Tadpole Galaxy is cosmic roadkill, a mesmerizing wreck where a smaller galaxy punched straight through its glowing disk, leaving behind a spectacular, star-studded tail. This isn't just a collision frozen in time, it's a living lesson in galactic violence and regeneration, showcasing how even the most brutal encounters can sculpt breathtaking beauty. The tadpole's most striking feature is its tail, a winding river of stars and gas stretching over 280,000 light-years, nearly 3 times the length of our Milky Way. Unlike the antennae or mice galaxies, where 2 spirals tangle symmetrically, this is a one-sided assault. Picture a compact intruder, perhaps a third the tadpole's size, plunging through its disk like a bullet through smoke. The gravitational shockwave ripped stars from their orbits, flinging them outward in a shimmering arc. But here's what's astonishing: that tail isn't just debris. Hubble's sharp eye revealed over 1,000 young, blue star clusters glittering along its length, stellar newborns, ignited as colliding gas clouds compressed under the tidal forces. Yet the real drama lies in what's happening to the tadpole's core. While its tail tells the story of disruption, its heart reveals resilience. The intruder's gravity funneled vast amounts of gas inward, triggering a firestorm of star formation around the central black hole. Infrared observations showed dust-shrouded nurseries churning out stars at a frenzied pace, a burst of creativity amid the chaos. Over time, this activity will calm as the galaxy exhausts its fuel. But for now, the tadpole thrives in its duality, a mangled disk birthing new stars even as its tail fades into the void. What makes the tadpole so special isn't just its appearance, it's its rarity. Most galactic collisions involve similarly sized partners, but minor mergers, where a small galaxy disrupts a larger one, are far less common. The tadpole offers a pristine example of how these lopsided encounters play out. Unlike the frantic star formation of the antennae, where both galaxies contribute gas, here the smaller intruder likely stripped material from the tadpole's disk, leaving behind a tail rich in the larger galaxy's stolen bounty. And then there's the future. Over billions of years, the tadpole's tail will dissipate, its stars scattering into intergalactic space or falling back toward the main galaxy. The intruder, now long gone, will have left its mark not just in scars but in rebirth. The tadpole may eventually settle into a new shape, perhaps an elliptical galaxy, its spiral arms erased by the encounter. But for now, it remains a celestial snapshot, a fleeting moment in the universe's endless cycle of destruction and renewal. So when you gaze at Hubble's iconic image of the tadpole, remember you're not just seeing a pretty space oddity. You're witnessing a galaxy caught mid-transformation, a testament to how even the most violent encounters can weave threads of light across the cosmos. And somewhere out there, another tadpole is forming, another tale stretching into the dark, proof that the universe writes its grandest stories in collisions. The Cartwheel Galaxy is cosmic graffiti, a dazzling, ring-shaped masterpiece painted by one of the universe's most precise acts of destruction. Located 500 million light-years away in the constellation Sculptor, this galaxy didn't start with a ring. It earned it the hard way when a smaller intruder galaxy plunged straight through its heart like a bullet through smoke. The collision didn't just leave a scar, it set off a shockwave of star formation so intense it redrew the galaxy's entire structure, transforming it into a rare celestial bullseye. What makes the cartwheel so mesmerizing isn't just its shape, but the physics behind it. As the intruder galaxy barreled through, its gravitational force sent ripples racing outward through the cartwheel's gas clouds, like tossing a stone into a pond. These ripples compressed the gas, triggering a frenzy of star birth that lit up the galaxy's outer rim in a blazing blue ring. Meanwhile, the central core, stripped of its gas by the impact, became a quiet graveyard of older, redder stars, a stark contrast to the youthful brilliance at its edges. Hubble's sharp eye captured this duality in stunning detail, revealing clusters of stars so young they're still wrapped in the nebulous glow of their birth clouds. But the cartwheel isn't alone in its ringed glory. Compare it to Hoag's object, another famous ring galaxy 600 million light-years away, and the differences tell a story. Hoag's object is nearly perfect, a symmetrical loop of blue stars encircling a golden core with a hauntingly empty gap in between. While the Cartwheel's ring is messy and still evolving, Hoag's appears serene, as if the violence that formed it has long since settled. Astronomers still debate Hoag's origins. Some suggest a slower, more ancient collision, while others propose a peculiar instability in the galaxy's own structure. Either way, the contrast between these two ringed wonders shows how galactic collisions are like snowflakes. No two ever unfold the same way. The Cartwheel story doesn't end with its ring. Peer closer and you'll spot tendrils of gas stretching beyond the main galaxy, ghostly remnants of the intruder's passage. Meanwhile, X-ray telescopes reveal superheated gas swirling around newly formed black holes and neutron stars, cosmic shrapnel from the explosion of massive stars born in the collision's aftermath. Even the intruder itself hasn't escaped unscathed. It's likely been stretched and distorted by the encounter, though it's now too faint to spot against the Cartwheel's glare. What's truly remarkable is the timescale. The collision happened roughly 200 million years ago, a blink in cosmic terms, yet its effects are still unfolding. The ring continues expanding at nearly 200 miles per second, its outer edge a moving front of stellar birth and death. In another few 100 million years, the Cartwheel's structure may smooth out, its ring fading as star formation slows. But for now, it remains a snapshot of cosmic violence caught mid-transformation, a reminder that even destruction can create breathtaking beauty. So when you look at the Cartwheel galaxy, remember, you're not just seeing a pretty spiral with a hole punched through it. You're witnessing a celestial phoenix, a galaxy reborn in the wake of catastrophe. And somewhere out there, another Cartwheel is forming, another ring lighting up the dark, proof that the universe never runs out of ways to turn chaos into art. The bullet cluster isn't just another cosmic collision, it's a smoking gun, a cosmic crime scene where the invisible fingerprints of dark matter were finally exposed. Located nearly 3.8 billion light-years away, this cluster, officially known as 1E0657-558, reveals something astonishing. When two galaxy clusters smashed together at millions of miles per hour, their dark matter and visible matter didn't just separate, they divorced completely, leaving a trail of evidence that reshaped our understanding. Universe, here's how it happened. Imagine two massive clusters, each containing hundreds of galaxies, hurtling toward each other. When they collided, the galaxies themselves, bound by gravity but mostly empty space, passed through like ghosts, barely noticing the impact. But the hot gas filling the space between those galaxies, that's where things got messy. Like two clouds of smoke slamming together, the gas particles collided and piled up, heated to hundreds of millions of degrees and glowing in X-rays. Meanwhile, the cluster's dark matter, mysterious, invisible stuff that outweighs normal matter 5 to 1, kept right on moving, unaffected by the crash. This separation was the breakthrough. By mapping the bullet cluster's mass using gravitational lensing, the way its gravity bends light from more distant galaxies, scientists could trace where the bulk of the mass ended up. Shockingly, it wasn't with the glowing gas. The heaviest parts of the clusters, the parts bending light the most, were offset, drifting ahead like shadowy prowlers. That mismatch proved dark matter wasn't just a mathematical fix for galaxy rotation speeds. It was real, tangible, and fundamentally different from anything made of atoms. The implications rippled through cosmology. If dark matter hadn't interacted with the gas or itself during the collision, it meant this mysterious substance wasn't just normal matter hiding in the dark. It had to be something exotic, particles unlike anything in the standard model. Overnight, the bullet cluster became the most compelling evidence for dark matter's existence, a cosmic experiment no lab on Earth could replicate. But the bullet cluster isn't just about what we know, it's about what we still don't. Why doesn't dark matter interact with light or itself? Could it be made of WIMP actions or something even stranger? Every new observation deepens the mystery. Some theorists even argue the cluster's behavior hints at modifications to gravity itself, though most evidence still points to dark matter's dominance. What's undeniable is this: the bullet cluster turned a theoretical puzzle into a visible reality. It's a reminder that the universe's greatest secrets aren't always hidden in the distant past or the quantum foam. Sometimes they're written in the wreckage of collisions happening right now in the dark between the stars. And as we stare at this cosmic bullet hole, we're left with a humbling thought: the stuff we can see, the galaxies and gas and light, might just be the tip of an invisible iceberg. 7 billion light-years away, where the cosmos stretches toward its ancient past, lies a titanic spectacle of destruction, the El Gordo cluster. Officially catalogued as ACDCLJ 01024,915, this isn't just another galactic collision. It's the heavyweight champion of the known universe, a merging behemoth so vast it defies comprehension. With a mass equivalent to 3 million billion suns, El Gordo isn't merely big, it's a cosmic anomaly, a gravitational monster whose very existence challenges our understanding of how structures form in the early universe. What makes El Gordo so extraordinary isn't just its size, but the violence of its birth. 2 galaxy clusters, each already among the largest in existence, are caught mid-collision, their gas clouds smashing together at millions of miles per hour. The friction from this cosmic pileup heats the gas to an unimaginable 200 million degrees, so hot it glows not in visible light, but in searing X-rays. Telescopes like Chandra have captured this radiation, painting El Gordo in eerie blues and purples, a stark contrast to the golden starlight of its member galaxies. But here's where the story twists. When scientists mapped El Gordo's mass using gravitational lensing, the way its gravity bends light from even more distant objects, they found something bizarre. The bulk of the cluster's heft wasn't where the X-rays flared brightest. Just like the bullet cluster, El Gordo's dark matter seemed to have slipped through the collision unscathed, leaving the hot gas behind like cosmic litter. This ghostly separation confirmed dark matter's elusive nature on a scale never before seen, proving that even in the universe's most violent crashes, the invisible stuff refuses to play by ordinary rules. Yet El Gordo's mysteries don't end there. Its sheer existence so early in cosmic history, just 6.5 billion years after the Big Bang, should be nearly impossible. Current theories suggest galaxy clusters of this size need far more time to assemble. One explanation: El Gordo might be the product of a hypervelocity collision, where 2 clusters slammed together with such momentum that their merger outpaced the universe's expansion. Another tantalizing idea: the cluster's bizarre baby fat could hint at exotic physics, like interactions between dark matter particles we've yet to discover. Peering at El Gordo is like looking through a cosmic magnifying glass into the past. Its light, billions of years old, shows us a universe far more dynamic and far more violent than we ever imagined. And as telescopes grow sharper, this colossal wreck continues to whisper secrets about how the largest structures in existence are forged, not in the gentle pull of gravity, but in the furnace of catastrophe. One thing's certain: in the grand tapestry of cosmic collisions, El Gordo isn't just a thread. It's the roaring needle stitching together the universe's most hidden truths. Deep in the hearts of colliding galaxies, where gravity twists space into knots and matter spirals toward oblivion, the universe's brightest beacons are born quasars. These dazzling cores of ancient galaxies outshine entire constellations, pouring out more light in a single second than our sun will produce in its entire lifetime. But their brilliance isn't just a cosmic light show. It's the death scream of matter being devoured by supermassive black holes, superheated to millions of degrees as it plummets into the abyss. And the trigger for this terrifying spectacle: galactic collisions on the grandest scale. Picture two spiral galaxies, each with its own supermassive black hole at the center, locked in a gravitational dance. As they merge, chaos erupts. Gas clouds that once drifted peacefully now slam together, compressed into vast, swirling rivers that funnel toward the black holes. The friction of this infalling material ignites temperatures so extreme that atoms tear apart, glowing with the intensity of 1 trillion stars. But here's what's wild: without galaxy mergers, most quasars might never light up at all. Isolated black holes often starve, sitting dormant with little to feed on. It's the collision-driven buffet of gas and dust that awakens them, transforming these silent giants into blazing engines of destruction. The numbers defy belief. A typical quasar can be 1,000 times brighter than the Milky Way, yet powered by a region no larger than our solar system. That's the terrifying efficiency of a black hole's appetite, converting up to 40% of infalling mass directly into energy, far outpacing nuclear fusion in stars. And the fuel for this frenzy comes directly from the wreckage of galactic mergers. Hubble images reveal quasars embedded in galaxies with distorted shapes, tidal tails, and double nuclei, all textbook signatures of recent collisions. Even our Milky Way's quiet central black hole, Sagittarius A, likely had a quasar phase billions of years ago, ignited by its own violent merger history. But quasars aren't just cosmic monsters, they're sculptors. The radiation blasting from their cores acts like a universal blowtorch, heating surrounding gas so intensely it can halt star formation across entire galaxies. This quasar feedback might explain why massive elliptical galaxies, the products of ancient mergers, are often filled with old, red stars and little new stellar activity. The quasars born from their collisions didn't just shine, they regulated their own growth, carving out the galaxy's future with bursts of energy so powerful they could expel gas entirely into intergalactic space. Yet for all their ferocity, quasars are fleeting. After a few million years, a blink in cosmic time, they exhaust their fuel and dim, leaving behind quieter but still supermassive black holes. The same mergers that birthed them also seal their fate, as the black holes at the hearts of colliding galaxies eventually spiral together and merge. These black hole mergers, detected by gravitational wave observatories like LIGO, are the final echoes of the chaos that once lit up the early universe. What's astonishing is how many dots connect back to these collisions. The quasars we observe in the distant universe, their light traveling billions of years to reach us, are snapshots of a violent, formative era when galaxies clashed and black holes feasted. Without these mergers, the cosmos might have remained dim, its black holes slumbering in the dark. Instead, collisions turned them into lighthouses, their brilliance piercing the void and illuminating the universe's most fundamental truth: creation and destruction are forever entwined. On August 17, 2017, the universe sent us a message, one written in gravity, light, and the birth cries of heavy elements. For the first time in history, scientists detected both gravitational waves and electromagnetic radiation from the same cataclysmic event. Two neutron stars colliding in a galaxy called NGC 4993, 130 million light-years away. This wasn't just a breakthrough in astronomy, it was a Rosetta Stone moment, decoding how the cosmos manufactures the heaviest elements in the periodic table, from the gold in your jewelry to the platinum in catalytic converters. When these city-sized stellar corpses, each more massive than our Sun, but compressed into a sphere just 12 miles wide, spiraled into each other, they unleashed a storm of physics so extreme it bent spacetime itself. The collision sent ripples through the fabric of reality, detected by LIGO and Virgo as gravitational waves. But unlike black hole mergers, which are invisible, this crash also produced an afterglow across the entire electromagnetic spectrum. Telescopes around the world swiveled to catch the fireworks, an initial burst of gamma rays followed by a fading afterglow of X-rays, ultraviolet, visible light, infrared, and radio waves. This multi-messenger event gave scientists something unprecedented, a complete autopsy of a neutron star merger. The real magic happened in the wreckage. As the neutron stars smashed together, their incredible density, a teaspoon of their material would weigh 1 billion tons, tore apart atomic nuclei, spewing neutron-rich matter into space at relativistic speeds. In this radioactive maelstrom, a process called rapid neutron capture, or the R process, forged elements heavier than iron almost instantly. Supercomputers later calculated that this single event likely produced hundreds of Earth masses worth of gold, platinum, and other rare metals, scattering them into the cosmos like seeds. But kilonovae, the name given to these neutron star collision afterglows, aren't just cosmic jewelry factories. They're also laboratories for fundamental physics. The 2017 event confirmed that gamma-ray bursts, some of the most energetic explosions in the universe, can indeed originate from neutron star mergers. It also provided clues about the nature of matter at densities so extreme that protons and electrons merge into neutrons, forming exotic states that defy earthly chemistry. Some theories suggest the merged remnant might briefly become a quark-gluon plasma, a primordial soup not seen since the Big Bang before collapsing into a black hole. What's truly astonishing is how this one event connected cosmic scales. The gravitational waves told us about the merger's dynamics, the light revealed its chemical fingerprints, and the gamma rays hinted at relativistic jets piercing through the wreckage. For the first time, we didn't just observe the universe, we eavesdropped on it in gravity, light, and nuclear alchemy simultaneously. And every new kilonova detection since then has added another piece to the puzzle, proving that the heaviest elements in our bodies and our technology weren't forged in the hearts of stars, but in the shattering embraces of dead ones. So the next time you hold a piece of gold, remember, you're holding stardust, yes, but stardust born from one of the most violent divorces in nature. A neutron star's death is the universe's recycling program, turning the ashes of ancient suns into the building blocks of new worlds, and perhaps one day new life. If the universe had a birth certificate, it would be stamped with the fiery signature of the Big Bang. But how will this cosmic story end? After eons of collisions building galaxies, forging stars, and birthing planets, the final chapter won't be written in creation, but in destruction. Scientists paint several grim possibilities, each more mind-bending than the last, and all rooted in the same violent forces that shaped our cosmic past. First, there's the Big Crunch, a poetic symmetry where expansion reverses into collapse. Imagine every galaxy, every star, every atom drawn back together by gravity's unrelenting pull. Galactic collisions, once rare spectacles, would become inevitable as the universe contracts. Andromeda and the Milky Way's merger would be just the opening act. Over billions of years, galaxies would pile up like cars in a cosmic traffic jam, their supermassive black holes merging into ever larger monsters. Temperatures would soar as space itself shrinks, until finally all matter compresses into a singularity, a mirror of the Big Bang where time and space cease to exist. It's a cyclical vision, suggesting our universe might be just one heartbeat in an infinite cycle of expansion and collapse. But the opposite scenario, the Big Freeze, feels even more unnerving. Here, expansion never stops, it accelerates as dark energy tears the universe apart. Galaxies would be ripped beyond the cosmic horizon, their light forever lost to us. Stars burn out, black holes evaporate via Hawking radiation, and matter itself decays into faint whispers of energy. The last collision in this lonely future might be two rogue protons meeting by chance after trillions of years, their impact barely a flicker in the infinite dark. This isn't just an ending, it's an erasure where even the memory of collisions fades into nothingness. Then there's the wild card, the Big Rip. If dark energy grows stronger over time, it could overcome not just gravity, but the very fabric of spacetime. First galaxies, then solar systems, then planets would be torn asunder. Eventually, even atoms would be shredded, their particles flung apart faster than light. In this nightmare scenario, the universe's final collision would be its own dissolution, a point where all structure, all history, all meaning is ripped into isolated fragments. Yet these apocalyptic visions share a profound irony. The same collisions that might one day destroy the universe also built everything we cherish: the gold in a wedding ring, the calcium in our bones, even the oxygen we breathe, all forged in stellar crashes and cataclysms. The universe's story isn't just about beginnings or endings, but the tension between them, creation rising from destruction and destruction lurking within creation. So as we gaze at the night sky, we're not just seeing the past, we're glimpsing a future written in collisions, some slow and stately, others unimaginably violent. And whether the cosmos ends in fire, ice, or silence, one truth remains: every collision leaves a legacy. Even in annihilation, the universe remembers. From the unimaginable fury of the Big Bang to the delicate dance of colliding galaxies, we've journeyed through 25 cosmic collisions that shaped everything we know. These aren't just random acts of destruction, they're the universe's way of building, transforming chaos into creation. Think about it, without Earth's cataclysmic encounter with Theia, we might not have our stabilizing moon or the tides that churn the primordial soup of life. Without the asteroid belt's shattered protoplanets, water-rich rocks might never have delivered oceans to our world. Even the gold in your jewelry was forged in the violent mergers of neutron stars, stellar ghosts colliding in the dark. On a galactic scale, collisions are the architects of the cosmos. The Milky Way's spiral arms, its star-studded bulge, even the rogue stars adrift in its halo, all bear the fingerprints of ancient mergers like Gaia Enceladus. Far beyond our local universe, titans like the antennae and mice galaxies show us how these slow-motion crashes birth new stars, ignite quasars, and sculpt the most breathtaking structures in existence. And let's not forget dark matter's cryptic role, revealed only when galaxy clusters like El Gordo and the Bullet Cluster tore themselves apart, leaving their invisible scaffolding exposed. But here's the most humbling truth: we're made of this violence. Every atom heavier than iron, the oxygen you breathe, the calcium in your bones, was crafted in the crucible of stellar collisions or the apocalyptic mergers of dead stars. The universe didn't build life gently. It forged us in chaos, hammering raw materials into existence through impacts of unimaginable force. So now we turn to you. Which of these cosmic collisions left you in awe? Was it the rogue impact that tipped Uranus onto its side, or the killer nova that sprinkled gold across the cosmos? Drop your favorite in the comments. We'd love to hear what sparks your cosmic curiosity. And if you crave more deep dives into the universe's greatest mysteries, don't forget to subscribe and hit that notification bell. The universe is full of secrets waiting to be uncovered, and we're just getting started.